Guys, welcome back to our machine learning class. Today we are going to learn a very important algorithm called as gradient descent. And once we finish, we'll see that actually gradient descent is not an algorithm, it is a framework. And though it has come into prominence for in context of neural networks, deep neural networks, but gradient descent was the master key always to find parameters of a model. At this point, you might be wondering what are parameters of a model. So slowly we'll find the answers to this together. So this is what we plan to cover today. We'll look at linear regression first, more in terms of how to find the parameters of a linear regression model. We'll look at different terminologies like model, hypothesis, parameters. We will look at different optimization methods, how to find the best model. We look at gradient descent in that context, look at its various varieties, and then finally we look at whatever equations we are talking about can be represented using vectors and matrices. If yes, is there a motivation for doing that? Okay. So let's go ahead and look at linear regression now. Let's revisit. So let's say on your x-axis, you have your TV advertising budget, and y-axis you have sales. So this is your independent variable, this is your dependent variable. Okay. So the task is that given a particular advertising budget for TV, what will be the corresponding sales? Now let's look at the picture. So this blue line is your model. Okay. So this is giving you the expected value. What are these red circles? These are your actual values. And what these blue lines are representing? These are representing errors or residuals with respect to each observation. Okay. And if you remember, we don't look at the residual in its correct value or exact value, but we take a square, because otherwise, here the deviation is positive, here maybe it is negative, and it can cancel out. Okay. So for the entire n observation, you can find out it like yi minus yi dashed square. Okay. So yi dashed is your expected value which comes from this line, and yi are your circles, and this is called your residual sum of squares. Okay. Now this is what we want to minimize, and yi dash can be is the straight line, so it can be thought as theta 0 plus theta 1x. Okay, almost in the line of mx plus c, but to generalize it further, we call it as theta 0 theta 1, and instead of RSS we call it as j. Okay, which is your cost function which you want to minimize, and your j is a function of theta 0 and theta 1. So I can write like j is a function of theta 0 theta 1, which is sigma yi dashed is represented by theta 0 minus theta 1 into xi square. So I can remove for ease right now the theta 0 theta 1. So do you remember, or do you recollect anything that how do we actually find theta 0 and theta 1? So we actually differentiate. We differentiate, take the first derivative and equate that to 0. And that gives us the values of theta 0 and theta 1. Okay. Now as there are more than one variable is there, so what we do is we keep one variable as constant, take the derivative, and we do the same thing for the other variable. Such kind of derivative is called as partial derivative. So we'll refresh very quickly some of the things about calculus. So one of the simple laws is called as power rule. So power rule is like, if you have x to the power n and you want to differentiate it, you get n into x to the power n minus 1. So as example, if you take x to the power 5, if you differentiate, you will get 5 into x to the power 4. And let's now look at chain rule. So basically, if you differentiate a function which is not a function of x but of gx, so then you calculate the derivative of f of gx, assuming like gx is nothing but x. Okay, so you find out f dash gx, and then you find out what is the derivative of gx with respect to x, and you get g dash x. So when I do that with respect to theta 0 and theta 1, this chain will be more clear to you. So let's look at a partial derivative example now. Okay, so let's say you have an expression like z equal to 3x square plus 2xy minus y square. So what you do is you do del z del x. So this will be 6x, this will be 2y, y square is constant, so you'll get a 6x plus 2y. Similarly, you can do del z del y keeping these x as constant. So let's extend this idea over here. So let's first do del z del theta 0. So we'll treat this like x square or like 2 theta square. So basically you'll find 2 into yi minus theta 0 minus theta 1 into xi, which is your gx. And then you find what is the derivative of this with respect to theta 0, which is minus 1, because yi will be constant, theta 1 into xi is going to be constant. So if we do some algebraic manipulation, we get an equation like this. Okay. Now, if we do the same thing with theta 1, here this term is going to be same. Okay, f dash dx is going to be same. But what about this? This will be derivative of this, or differentiation of this. So I will get a minus xi for this. All right. So again, I will do some manipulation and I will get an equation like this. So these two equations are called as normal equations, which can be used to find out the value of theta 0 and theta 1. So, these are two linear equations, and like simple methods like substitution, you can find out the values of theta 0 and theta 1. Let us say you are given a problem where you are given this x and y. So at the first step, you calculate this xy. Second step, you calculate x squared. And then these are your sum. So basically, you can put that in the equation and find out the value of theta 0 and theta 1. I hope you understand what is n. N is nothing but the number of observation, which is in this case 7. Okay. So we see a method by which we can find theta 0 and theta 1 such values which minimizes residual sum of square or j. Okay. Now in terms of machine learning, you call this theta 0 plus theta 1 x, or represent that as h theta x. Okay. This is your model hypothesis. Okay. The parameters are theta 0 and theta 1. Cost functions are j theta 0, theta 1, which you can represent like h0 xi. Okay. So this notation we will understand further. Your goal is to minimize j theta 0 theta 1. Okay. Or your goal is to minimize j and find the corresponding values of theta 0 and theta 1. Now it turns out that there are two principal methods to find out theta 0 theta 1. One way is called as closed form, by solving using a normal equation where there is a specific mathematical equation for that. Okay. So one problem with this is that when you have lot of observations and lot of features, when you load that in memory, it takes a lot of space. That is number one problem. Number two problem is that it takes around complexity of O n cube. Okay, so it takes a lot of time also to find out these values. Okay, so for that you have some approach called as an iterative approach. So what you do is you start with some values of theta 0 theta 1, you calculate j corresponding to that, and then you do some trial and error and you try to find out where j gets minimized, and gradient descent actually falls into this category. Okay, so if we look at this particular demonstration, so M and C is nothing but your theta 0 and theta 1. So you start with a random value, then you slowly adjust so that J is getting reduced, and you can see that initially the changes are very abrupt, and as you are closer to the optimal value, it is very slow. Okay, so such a behavior is called as a convergence, where it goes and stabilizes. Okay, all right. So now this theta 0 theta 1 are called parameters. They are also called as weights. Okay, so you understood that I need to change iteratively the parameters of theta and calculate j. Will it be completely arbitrary? No, not at least by your gradient descent method. So in gradient descent method, how the weight update happens is you find out the partial derivative. For simpler notations, we are using this, delta theta 0 and delta theta 1. So if I have a value of theta 0 old, or theta old, I can use that with this partial derivative to find the new theta. So we use another parameter called as alpha, which is a constant in this case. We use it with respect to delta theta 0, and if this is your old value, I subtract this product and get the new theta 0. Same goes for theta 1. For sake of generality, let's call it theta. And you might be wondering that such a scheme, will it take me towards the minimum value of j? So let's see. So let's see, or let's say that you have a theta value here, okay? And then let's say you are increasing theta by little bit. If you increase theta by little bit, what will happen? J will also go up, okay? So your del j, del theta both are positive. As a result, this will be positive, okay? So this entire term will be negative. So your new theta 0 will be less than old theta 0. So in this case, you will go towards this side, okay? And if I take another example, let's say theta is over here. Now, if I increase theta a little bit, j actually goes down. So del j is negative and del theta is positive. So this term overall is negative. Negative into negative will result into positive value. So theta 0 new or theta new will be more than theta old. So I will move towards this direction. So essentially, I am anywhere in the plot, anywhere in this J card, I will go and go towards the minimum value. Okay, that is the idea. Now, this is formalized in gradient descent algorithm. So we initialize the weights, we calculate the gradients, then we update the weight. Okay, by it is often represented by neta or alpha. Okay, and we repeat it until cost JW stops reducing. There can be some other predefined termination criteria as well, where maybe the change is below a certain amount of time, or you have certain number of iterations already predefined. Okay. So now we will look at the effect of alpha. So effect of alpha actually tells you how quickly you will move towards the convergence. So if you have small alpha, it will very slowly start going towards convergence. Okay, so that is how the behavior will be. So then you might say that why I will work like this rather than that, why don't I make alpha very big? So you can run into another problem like this. So maybe you start from here with a high alpha value, you jump over here, then again you go here, again here, then here, and you can understand that this is not also a behavior you want. And it turns out that there are algorithms which actually can start with very high values of theta, so some amount of random movement initially or some amount big steps initially. Then once you are closer to convergence, rather than the big steps, you have small alpha, small learning rate, you don't need to learn so much anymore. Okay, so these type of algorithms are called simulated annealing, which is a beautiful meta heuristic algorithm. I will urge you to read more about that. Okay, now your next question may be that you are oversimplifying the problem and you are assuming a cost function which is kind of parabolic. Okay, what happens if I have a function like this? Okay, so I start over here and then I can get stuck here, and I can see that this is not the lowest value of j, this is just a local minima, whereas I want to reach here, which is a global minimum. On the other side, I can start over here and slowly after some time, then there may not be any change happening at all. So I am in a plateau. Okay, so this can be a problem. Now, luckily for us, the problem that we are dealing with, MSE, minimum square error, is a convex function. So your next question may be that what has convex function to do with here? So actually, convex functions has a shape like this, where there is only one global minimum. Whereas if there is a non-convex function, there will be local minima. So based on where you are starting, you may reach a local minima, and of course there will be global minima. So when you are applying gradient descent or any other algorithm. So it is very much encouraged to look at the loss function or the cost function, basically the nature of J, whether it is convex or non-convex. Okay. So now let's look at the different variants of gradient descent. So the question is, when do I update my parameters? Okay, when do I update my W or theta? So one thing can be, you can do it for once you have calculated the change for entire training set, then you do it. So this method is called as batch gradient descent. Another extreme is you are doing a stochastic gradient descent. So basically here, you are doing the changes or weight update after you have evaluated every observation. In between, you have mini batch gradient descent where you are not working on one observation or on the entire training set. Okay. So from comparison wise, batch gradient descent calculations will be very slow, but its path to convergence will be more stable. Whereas stochastic and mini batch will be faster, but their path will be more erratic. So let us look at this graph now to understand that further. So theta 0, theta 1 are your parameters, and let's say this is where you have the optimal value of j theta 0, theta 1. So this batch gradient descent, which is this blue line, you will see that is stably moving towards that point. Whereas if you take mini batch, you will see that there are quite a lot of ups and downs, and then it reaches here. And if you take stochastic gradient descent, you can see that it is much more erratic, and you reach over here. Okay, so one thing is, of course, you will say that then we'll go for batch gradient descent. So essentially, if you go for batch gradient descent and it is a non-convex function, then batch gradient descent will reach a local minima, whereas stochastic and mini batch will have tendency not to get trapped at local minima. Okay, now let us look at the matrix operation or vectorization part that I was talking about. Let's say you are given test set which has n observation and which has got k features or k independent variables. Okay, the parameters are computed. You know the values of theta 0, theta 1. You now want to predict the values of testing set. Okay, so I can do it using our programming language, simple for loops. So I have number of observations for I equal to 1 to n. I initialize a variable called temp with the intercept or bias value. Then for each one of the features, I multiply the feature value with the corresponding parameter value, corresponding theta value, and update it and add it back. So this is how I get my actual prediction, because what I want is theta 0 plus theta 1 x1 plus theta 2 x2 like that. So I'll run the loop like this. Okay, so now please note that this theta can be considered as a vector. Okay, so where the bias term is theta 0 and feature weights are theta 1 to theta n, and every observation can be also taken as a feature vector which is x0 to xn, where x0 is always equal to 1. Why x0 is equal to 1? Because it corresponds to the bias term. Okay, there is no feature as such, we are just adding a dummy feature with value 1 for all the observations, and this is a vector. If you look at the entire test set, that will be a matrix. And what will give theta t and x, what it will give? So in original form, theta is a column vector. So if you take a transpose and multiply it, okay, then you will get things like this: theta 0 x0 plus theta 1 x1 plus theta 2 x2 up to theta n xn. And as x0 is 1, this will become theta 0. Okay, so this can be magically converted to one line now. Okay, so y hat, which is your predicted value, is theta t into x. So x can be for one observation. If you take the entire test set, then you get the predictions in one shot. Okay, and let's say now, can this be extended to the minimization techniques that we discussed in context to gradient descent? So essentially, we will start with your finding minimum square error, which is represented by x and h theta, and this is your vector notation. So if you apply those rules of partial derivatives on this matrix, what we will get is we'll get the normal equation in this form, where if we are given this matrix X, we are given this matrix Y, and we can do some matrix operations like transpose of X, then we can multiply transpose of X with X, take its inverse, again multiply with X transpose, and we get back the parameter vector. So this is what approach? This is the direct approach or closed form. What about the iterative part? So iterative part, similarly we need to do this, theta next step. So here we will be interested to find out this minimum square, the partial derivative of this minimum square, okay, minimum square here. So if you do that, this is what comes out, quite similar to what we have seen, okay. Only thing is that we are keeping the constants over here, and this del MSE is nothing but a vector which consists of derivatives of MSE with respect to all of theta 0 to theta n, and these in a vectorized format can be represented by 2 by m x transpose, and you multiply that with x theta minus y, okay. So these are the two formats. Now an obvious question is that this doesn't look that it is simplifying the problem or simplifying our understanding. Why do I need to do this? So actually there is a particular type of computer architecture which is called as SIMD, or single instruction multiple data architecture. So what happens here is that actually you have same type of operation, same instruction that you are applying on multiple data, okay. So let's take an example. Let's say you want to do an element wise operation between these between these vectors, okay. And if you use your loop, then what will happen is this operation will be element wise sequentially, okay. But if you represent it in a vectorized format and your processor supports this SIMD extension, it will happen in one shot. It will parallelly compute this and find C1, okay. So currently the GPUs have this SIMD operation which makes things much faster, okay. So that is the reason or motivation for looking at vectorized formats. Thank you so much for watching this video. I will be very happy if you put your question on the comment section, and I will try to go through each one of them and answer. Thank you once again for watching this video.